কোথায়?
আস্তে আস্তে।
I think we are live. Are you seeing on your phone?
One second. Like yes.
Hello? Okay. Hello everyone. এখন তো I think it's just you. We'll wait for users, no? We'll start in a few minutes, folks. We are just waiting for some more people to show up. And then we'll have a start. Yeah, so people are joining in. If you have a question about AI that you're curious about as you are sort of like coming into the webinar, you can type that out, because we are just waiting for a few minutes for more people to join, to give folks a chance to join. And in the meantime, you can type out any questions that you have. So maybe, that will help us sort of like, as we are moving through the webinar, we'll be able to answer some of your questions. I'll be able to answer some of your questions as we're going along. Yeah. This is the first live I'm ever doing. So, yeah. So 7:05, we'll start precisely at that. Yeah. If you have questions, please type out questions about AI, questions about AI ethics. We're going to start about in a minute. Okay, it is 7:05, so let us get on with the webinar for today. So, I'm giving a series of 2 webinars today and then on Friday on a brief introduction to AI ethics, in which we will try to confront some of the myths, some of the hype, and some of the harms that are associated with AI technologies. So today is the first in this series of 2 webinars, and this one is on demystifying artificial intelligence technologies. So we'll try to sort of like unpack these technologies a little bit more, because that's what's going to help us understand the harms and the ethics that are associated with these technologies. But that will be addressed in the second webinar on Friday. I am Aisha. I'm an associate professor at Homi Bhabha Center for Science Education at the Tata Institute of Fundamental Research in Mumbai. These webinars are produced as part of as an open education resource. I'm part of this EduScope 2025 project, and so I'm developing this as part of that. And I want to acknowledge in this work Ree, who has helped me in design and technology for producing this resource. Ree is also here with me. She is moderating the comments on YouTube. She'll alert me if you folks want me to stop and address something. For example, she might also be addressing some of your comments. And I also want to acknowledge a few other folks, discussions with whom have helped shape my perspective that I'm going to present. So the first thing that I want to talk about is that when we are thinking about the ethics of AI technologies, that is really connected to understanding what AI technologies are. If we don't understand what these technologies are, then we also can't really understand what the ethical issues with these technologies are, right? And so the first task that we have in front of us is demystifying AI technologies. So what precisely is AI technologies, right? And so that is our first task here. And so AI technologies, in order to understand what these are, the first thing that we need to understand is that they are some kind of an automation. Like a machine does something that a human was doing, right? That's something like a machine does. A human being grinds something, a human being writes a letter, a human being makes an image. Automation is something where a machine is doing something that a human being is doing. So if you want to understand it in detail, this automation can be hardwired. For example, it can be electrical mechanical systems. Our kitchen blender is a kind of an automation. So we sort of like plug that machine into the wall, it gets electrical power, and the blades whir. So it's producing some kind of an output. All machines are doing this. Similarly, a large cement mixer, that's also like a really giant blender, right? So these are hardwired. There are certain kinds of automations. We have known these for a really long time, right? And in some sense, AI technologies are sort of like an evolutionary stage in this process of automation, right? But we have to understand it as any other technology, not as some special kind of a technology, right? Because that's when we give into the myths surrounding it. But automations can also be done. Sometimes they're not hardwired. Sometimes they are algorithmic, in the sense that there's a program, there's a computer that is doing something, right? But what that computer is doing, those rules are written by humans, right? So humans are writing up or thinking up the rules and the steps, and they are telling a machine, in this case a computer, they're writing it up so that the computer is able to carry out that steps. And what does that lead to? That leads to things like, for example, automatic spelling check. This is something that many of us are familiar with. If we are writing documents, if we have a spelling error, then little red squiggly lines will appear below the words where there is a spelling error. And you can imagine how somebody could set up a database of all of the words in the English dictionary, right? And those are the rules. And so now When somebody is writing AHD, that is getting checked against those rules, the words in the dictionary, and there's a spelling error because it doesn't match any of the words. And so little red lines are generated under that word, right? Similarly, there can be more complicated set of rules. So this comes as an example of Eliza. That was the first ever chatbot. These days we are using AI in chatbots a lot. This was the first chatbot, right? And it did things like this. If the user said, I feel sad, the chatbot will write an output. Why do you feel sad? If the user says, I am worried about my job, then the chatbot would say, what does your job mean to you? But you could actually switch these words around, and so that gives you a feel for what the rules might be. So a user could say, I feel angry. And Eliza would say, why do you feel angry? Or happy. Eliza would say, why do you feel happy? It's just switching out that word. When it encounters a rule like, when it encounters a phrase like I feel, it is using a rule that, well, output the text, why do you feel? With that same text that follows I feel, right? I'm worried about my job, I'm worried about my career, my brother, my family. What does your job or your brother or your family mean to you? Yeah. So it's based on these rules. And yet, people actually got confused. People really started treating Eliza as if they were talking to a human, and they just wouldn't believe it even when the creator is telling that no, these are just rules, right? And so these chatbots can feel to us, even though Eliza was not doing any amount of thinking. It was not doing any emotional reasoning either. It was not trying to feel emotion or empathy or anything. It was just plain rules that were written up in a program. And still, people really felt that, it was giving them therapy, And, there was a sort of like a revised version of it that was generated in 2005, and it get into more complicated conversation, right? That is something troubling you, right? It will ask a user, is something troubling you? And somebody is saying, okay, the user is saying men are all alike. And Eliza is saying, what is the connection, do you suppose, right? And some of these things could be that after saying is something troubling you, you will always ask, what is the connection, do you suppose, right? So these are rules based. And so that is one level of automation that can happen, right? But the fun really starts happening, the phase that we are in, is when these rules or these steps are not these simple rules or steps that you, for example, saw in the Eliza chatbot, right? Rather, these rules or steps are based on patterns in very large data sets, right? So there are very large data sets, and we are trying to figure out what the patterns in these are. And actually, even this process by which these rules are generated, there's an attempt to get it automated. But as we'll very soon see, that people are really, really involved here. There are a lot of people who are involved in the generations of these rules and steps, even if they are not actually just thinking up directly what these rules are, right? So what are these systems where the rules or steps are based on patterns in very large data sets? We have seen some of these, or I'm hoping that you are familiar with some of these. For example, there could be recommendation systems. And so these are screenshots, for example, from my Instagram, where they're suggesting, in the first one, where they're suggesting who I should follow, right? Suggested for you. And then here is another one where a post is suggested to me, right? So how are they making out these particular suggestions? Other people are going to get different kinds of suggestions. So these are automated recommendation systems that are generating a profile of me and then generating some kind of a recommendation for me, for people, or for posts that I might like, right? Then there can be language translation and speech recognition systems. So here's for example, Google Translate. Here's a screenshot of that, right? And if I enter some text that is in Bangla, it will be translated into some text in English. And you can see here below that already there's also like a Hindi version of this Google Translate that is showing up here. And there's a mic here. So I could also, for example, press that mic, and instead of typing in the text, I could speak the text in Bangla, and the system will recognize that speech and try to enter sort of like words that I'm speaking, right? So these are systems that are based on patterns in very large language data sets, for example, right? Then there can be classification systems, right? So here's a photograph from Google Photos, and what they are saying is, organized with the help of AI. So my photo documents can now be automatically sorted into albums like screenshots, receipts, notes, and more. And it can categorize similar photos together with photo stacks, right? And they're explicitly labeling it with the help of AI. So this is an example when they are trying to classify many things together, which are all the things that fit into a folder together, for example, right? And that process is being automated. At least for the user, it feels like it is getting done by a computer, right? And then there can be text and image generation. So this is something that has really caught our attention, right? So ChatGPT is the thing that made AI as a household term to many people, where text and image are getting generated. But again, this is only an example of the same. The algorithm is working on patterns that are based on very large data sets, patterns in very large data set. So it's trying to do that, and we'll understand some of the process for how this generation happens, right? And an application of this, of course, is the ChatGPT, but also look, for example, in Amazon. Here's a screenshot from a product in Amazon that I was interested in, and what they're saying is that there's a summary of all the customer reviews, right? And this is generated from the text of customer reviews by AI. So Amazon's AI is reading or inputting all the customer reviews and then outputting some summary text. Here's an image. Midjourney is a software that, for example, can generate images. And here's an image of, it's a fake image, right? It's an AI generated image, and it's showing that President Trump is getting arrested, obviously fake. But also notice how in this region, it's very hard to tell whose foot and whose leg, and that kind of, it just fuses different legs and hands together, right? And that's partly because, again, these are based on analysis of large data sets. And you can imagine that, if you have lots of pictures of these sort of like grapplings with the police, it'll be hard in those pictures to always tell the foot and the leg. And so when AI is sort of like consuming those pictures, and it's also generating pictures where it's hard to tell where the leg is and whose leg it is. But it's fairly randomly generated here. So that's text and image generation work. And some of the most important work that is happening with AI that gets hidden, that doesn't always sort of like come to the public view. We are fascinated by things like ChatGPT and generating an image, right? Or somebody can automatically write my meeting notes, right? But somewhere else where some of these automation technologies are going, which we really, really need to attend to, is, for example, courts can use automation. Lots and lots of cases, right? Courts don't know what to do, and so what they want to do is they want to put a machine that will tell which cases the courts should take up and which cases the courts don't take up. Police, for example, can use automation also to decide, where should they send their surveillance patrols most. And police are using these kinds of automation software in order to make some of these decisions, right? Similarly, banks can use automation to decide whether a person should be given a loan. All of these are based on large data sets. So courts will use all of the data that has happened in the past about, which cases they did take up and which cases they triaged. They will feed that into a machine and try to look for patterns. Police will feed the data on where they have in the past made arrests or done such patrols, and based on that data they will try to make a machine make future predictions of where they should be posting, right? And similarly for the banks. So these are all types of automation which are rules or steps, are based on patterns in very large data sets, and these are the technologies that are advertised as artificial intelligence technologies, right? This set gets labeled in the market as artificial intelligence technologies, right? But the first mythology that we need to confront here is that even though artificial intelligence technologies, we are saying that a machine does something that a human was doing, but actually when we look very closely, it's always workers who are sustaining the automation, right? Those are actually the people who are making these machines tick, and we're going to understand a little bit more why. But let's look a little more closely where we are finding this out, why AI is such an advertisement term rather than something where actually it is automated, right? And so, for example, if you are looking at this is this Waymo car, which is advertised as a self-driving car, right? But actually, when we look at the reports, what is happening is that Waymo has a set of people located remotely who are monitoring the different cameras and sensors of the car and ready to take action if need be, right? So there's an army of people who are sitting and monitoring these cars as they are driving on the roads, even if they're being billed as self-driving, right? Similarly, when we look at ChatGPT, the report came out, this is from Mind Matters, that OpenAI evidently employs 40 humans to clean up GPT-3's answers manually, because GPT-3 does not know anything about the real world. So what is happening is that when GPT's answers sometimes are just really inappropriate, and ChatGPT is employing bunches of humans to manually clean up these answers, right? So not quite as automated as we want it to be. And then here's one more example, Amazon Fresh. So these stores went very fancy and very viral. You can just sort of walk into the store and you can pick up what you want and you can just walk out. You never have to interact with a person. And you never have to sort of like bring out your cards or pay anything. It's just automatic, right? Just walk out. But turns out when people looked very closely at it, there were more than 1,000 people in India who were working on these stores, and their jobs were including manually reviewing the transactions and labeling the images from the videos, right? If we there's this new movie on Netflix, Humans in the Loop, and one of the scenes in that movie actually is of when the data workers are sort of puzzled as to whether the grocery item that a customer has picked up in one of these stores is turmeric or ginger, right? And so they're trying to decide which one is it, right? And so really it's not automated. It's a bunch of people sitting behind cameras, right? It's not artificial intelligence in that sense. It is human intelligence of people who are working in exploited conditions, of people who are working at very low wages, of people who are working very long hours, and who are peering from behind cameras in order to create this illusion that these systems are automated when they are not really automated in that sense, right? In fact, Amazon went one step ahead, and what they created was Amazon Mechanical Turk, a subsidiary company, and what that does is look at how they advertise it. Access a global on-demand 24/7 workforce, So always available workers, 24/7. They're always on demand and they're global. So they have to be global because they're situated in countries where the labor laws often allow companies like Amazon Mechanical Turk to exploit the workers, right? But a large number of data workers are involved in the design and implementation of these automation systems. And if we are thinking that, maybe it's a modern thing that these amazingly, evil companies are doing this, well, there's a history of people trying to fool us into thinking that a machine is doing something that a human was doing. This is an example of, something that was originally called the Mechanical Turk. It was built in 1770s. And it was a machine that was purported to say that it'll automatically play chess with you, and many good players of chess were losing to the machine, right? Turns out that inside the machine where those doors are open, they had put in a chess master who was able to see the opponent's moves through a clever mechanism, and then was able to move levers in order to move the chess pieces. It wasn't automation at all. It was a clever trick by which a person was able to hide, so that the person can make the pieces move without the other person being able to tell that it's a person. It'll look like it was a machine. It's a parlor trick. And so are most of these other devices. They are, in some sense, parlor tricks. And I think we made one mistake here. This needs to flip. Yes. Okay. We are back in action. So a lot of this work about that, for example, people are involved behind making AI tick. Data workers inquiry is something that I want to draw your attention to. They are doing a lot of work in visibilizing the data workers, in making their work visible and making them part of the research and the design of these systems, right? So that they can be better and that they can work for the people rather than for the corporations, right? So that was our first sort of like thing to understand, that workers are what sustain automation. But before we can get to the other points of demystifying that AI is not how humans learn, we first need to understand how these technologies are designed and produced. So we're going to go a little bit into the design and production of artificial intelligence technologies, right? And for this, let's zoom here. We are going to work with this system which is called Quick Draw, right? And this is a kind of a game system that Google has designed. It's called Quick Draw, and this is how they start out. Can a neural network learn to recognize doodling, right? Like if you're doodling with a pen, can a neural network learn to recognize it? And saying, help teach it by adding your drawings to the world's largest doodling data set, shared publicly to help with machine learning research. So what we're going to do is we're going to go over to Quick Draw and play a game, right, to see how this neural network system behaves with us, right, and what we can learn from just sort of like seeing how this system is operating. So I need to make a little switch, so give me a second, right? Quick Draw scene. I'm shifted to Quick Draw scene. Yes. So here's we are in Quick Draw. Help teach it by adding your drawings to the world's largest doodling data set. Let's draw. Right? And so it's going to give me 6 drawings. Drawings 1 out of 6. It's going to give me 6 drawings, and each drawing I have to draw in under 20 seconds, right? And you'll see what the system does, right? So I'm gonna press got it, and then I'm gonna go and start drawing, right? So it said rainbow, so maybe I'll draw like this, and like
Oh, I know,
this.
it's rainbow.
So it says it's rainbow, right? So you saw what it did. I was drawing, and then I heard the words, it's rainbow. Let's try and get the next one, onion.
I see nose, or water, or pear. I'm not sure what that is. Oh, I know, it's onion.
So we'll play the next one. I want to get to the end of it. I want you to notice carefully what are the words that are coming out, what you're seeing on the screen. Bench.
I see line. Oh, I know, it's bench.
Lion.
I see potato, or computer mouse. I see pear, or vase, or peanut, or ring, or gear. I see mouse, or sea turtle, or planet, or trombone. I see trumpet. Oh, I know, it's lion.
And then vase. Drawing 5 out of 5.
I see nose, or squiggle. Oh, I know, it's vase.
And then traffic light.
I see leg, or line, or wine bottle, or skyscraper, or marker. I see remote control, or sleeping bag. Oh, I know, it's traffic light.
And so, well, here's the results that we get. Our neural net figured out 6 of your doodles. Select one to see how it figured it out, and visit the data to see if it. So here it selected, it got all of the doodles really right. On like it could recognize that. So we saw what it did, and when I click at visit the data, this is what the data looks like. What do 50 million drawings look like? Right? So this is the data of all of the database. Actually, before I do that, I want to go back once and look at one of the drawings that sort of like, let's look at onion, for example. And so it says, you were asked to draw onion. You drew this, and the neural net recognized it. So here's a picture of the onion I drew. And it says, it also thought your drawing looked like these. So it says that the first one is the correct match, the onion. And then it gives some drawing of not my drawing, obviously, some other drawing, right? And then it says second closest match, and that's a pear, right? So if onion was not a match, well, the second one in line that it was thinking was pear. And then the third one in line was pineapple, right? So it wasn't just onion. It was like 3. The top choice was onion, which was the correct match, right? And there are all these drawings. So I want to now get back quickly into Excalidraw and try and see if we can understand how this system is really working and what might be going on behind it, right? And so I'm going to make a switch again. So give me a second. Okay. So we played that game, we saw what it did. And so what I'm going to do here is try and analyze a previous gameplay that I had done before, right? And in that gameplay, it recognized 4 of my doodles and saw something else in the other 2, right? And so there it had given me a cat, a pickup truck, a pond, a mouse, a bracelet, and a pea, right? And cat got recognized, pickup truck, mouse, and pea, but pond and bracelet were not recognized, right? I don't know why, but it saw something else in the other 2 is what it is saying, right? And so let's look at the first one a little bit more closely. What was it doing when I drew this cat and it said, oh, I know it's a cat, right? So what did it do? So results from the first prompt, draw a cat. That was the first prompt that I got. I've done these screenshots from the previous play, and that's why I'm sort of like using this one rather than the one that we just played, right? And so this one here, you were asked to draw a cat. You drew this. And here it is saying, just like for the other one, I'd shown that, there were multiple matches. Here also for cat, it also thought your drawing looked like correct match cat, but also the second closest match, which was an ant. And here's some diagram, right? And then the third closest match, mosquito. And again, some picture, right? So this is what happened when it saw, for example, there's a cat. So let's take a look more closely, right? So what happens is something like this. It's not like I draw a cat and it immediately said, oh, I know it's a cat. There were a lot of missed turns before it reached, I know it's a cat. So for example, it produced a lot of answers in between, right? Before guessing the correct answer. So input was like this cat goes in, and what we see really is the ball, road, tree, cookie, and then it says, oh, I know it's a cat, right? But of course, right, it wasn't as if this cat sort of like went in, the drawing of the cat went in as a whole, right? There was a process. I was trying to draw it, and so And while I was drawing it, it was guessing like ball and road and tree, right? So how does that happen? We need to look a little more closely inside this machine, right? So let's go inside this machine. There's the player, that's me, right? And there's the game interface. This game interface is doing things like telling me draw a cat, right? And so I draw a cat and I'm putting it into the game interface, the website that I'm interacting with, right? But this website is behind the scenes also interacting with a neural network, right? And so what it is doing is this image of a cat that I've drawn at this moment, I haven't been able to draw the full cat yet. I've only been able to draw the face, right? I've gotten the prompt, draw a cat. Imagine that we are, maybe 2 seconds in and I've been able to draw this little bit, right? And so what it's doing is in real time, the game interface is sending this to a machine called a neural network. It is processing it in some way. That's what I'm showing as the grid. And then it's sending to this machine. And what this machine is doing is this machine is programmed to calculate the probability. Right? For what probability? For whether, how can we label this drawing? So it has a set of words. It has lots of words, some 345 words, right? And they can all be the label for this machine. It doesn't know what they can be. Right? And each of these words gets a probability. So for example, if there was a list of these 345 words here, right? The first word is ball, right? So that's the highest probability word that it has come up with, 90%. And then maybe plate, 87%, and potato, 85%, right? So it has assigned probabilities to each of these words. It has calculated those things. And so next thing in the process is we compare. Well, the prompt was draw a cat. You compare cat to the top label of ball. And if there isn't a match, then what the system does is it just exits what the ball is. All of this is very complicated in some senses. But I think what we can do is like understand this cycle, that there's a picture that is going in, there's some probabilities that is getting calculated. It takes the highest probabilities and says, well, is that highest probability cat? Well, if it is not a cat, then write out that word, because whoever the player is, they need to know that it had made a guess ball, even though that is incorrect. So then the player, that is me, I end up drawing a little more of the cat, right? So I've been able to draw a little bit more. And now it generates a different set of words because more of this cat has gone into this neural network. And so it has regenerated a calculation. And now it is saying, well, maybe the highest word is like road. And the next highest word is river. And then the third highest word is horse for this picture that has gone in. Again, it compares cat with the top word that is road. And again, not a match, right? So road is not cat. And so road is outputted. I get a little more time, and so now I have drawn the full cat. The tail has also come in, and now suddenly something changes. The calculation, again, the same thing, the calculation has changed, but now cat has appeared as the highest probability word, right? The word that is most likely to describe this picture from among the words that the neural network has access to is cat. And so there's a comparison of that. And so, yes, there's a match. And so now it outputs a different sort of like words. It says, oh, I know it's a cat. That's what we get to hear, right? So that's partly what is going on in this game network, is that it is making these guesses. It is making these guesses of these words. And then, oh, I know it's a... But how are these probabilities calculated? How are these numbers calculated, right? So for that, we'll have to zoom in a little bit more. It's going to get a little more complicated. So bear with me a little bit. And if some of this is complicated, you can put down your questions in the chat. And we can address it during the talk. We can type out responses to that later. So, but don't be intimidated by so much of these numbers. Let's try and get through some of this. And this will help us understand some of the ethics, trying to get through some of the mathematics of it. That's my claim. So we'll see how much of that works. Okay, so here's the thing that happens. Once we have this cat drawing, what the first thing that the system is doing, that this machine is doing, is converting this cat drawing into a bunch of numbers. How is it doing that? it is putting all of these grid marks on top of the cat. So we get all these little tiny pixels, right? All those little tiny squares that we get, and each of those squares get a value, right? Either that value is 0 because there's nothing in that square, or maybe there's a line or a gray line in that square, and so it gets some kind of a number that is based on what is in that little tiny squares, right? So the first thing is the image is converted into these numbers, right? And often this conversion of image into numbers or text into numbers, it's a complicated process. It needs a varieties of different kinds of things that you need to do to process the data. But at the end of it, you take your text, or you get numbers that you can put in, and these numbers are then assigned to the first layer of the machine. So imagine the machine that is doing this computation almost has these, these layers, these long layers, and numbers get filtered through these layers. This process of this number calculation, how actually nobody really understands how this happens, right? And I'll tell you in a moment why nobody understands. There's various kinds of calculations that keep happening in these layers, and we can try to explain some of it, but it isn't the same kind of thing as, for example, if I say that you have a cup of tea and you put in 1 teaspoon of sugar, and then you put in 2 more teaspoons of sugar. So how much sugar do you have in a tea? You have 1 plus 2 equals 3, right? That's something that we understand. We make sense of it, right? But how these numbers flow, we can't make that simple sense of it. But still, I'll try to walk you through some of this. So first, the image is converted to numbers. Then the numbers are assigned, they're inputted into the machine. And inside the machine, there are many more of these, which are called nodes, or you can imagine that they're variables, they store values or something like that, right? And what is happening is that these numbers that are getting inputted into the machine, the input layer, first layer, they are multiplied by other sets of numbers in particular patterns. For example, the first number is the first blue number is only multiplied, is only contributing to the first 3 green numbers, right? The second blue number, for example, is not contributing to the first green layer, and so on and so forth. So there are all of these different connections that are either there or not there. Each of these connections has another number associated with it, and so when it is going there, it is getting multiplied, right? And then this green node gets another number, and then that number gets further propagated into the machine or not based on certain other kinds of criteria. At the end of all of this sort of like processing of numbers, somehow each of these words that are there for the output layer of the machine, like road and ball and ant and mosquito and cat and all of these different kinds of numbers, pickup truck, right? They all get a number. Each of them ends up getting a number, and that number is telling us how likely is it that that word, what is the chance that that word is a good describer of the image that we get, right? So that's what the system is doing. It's trying to match if then this one matches with the prompt that we got, right? So complicated numbers, and that is the point of it, that there can be these billions of nodes and trillions of parameters in this machine. So we can't keep track of them the way I would if I was adding up, say, teaspoons of sugar, right? Or if I was trying to figure out how much something is speeding up or slowing down, right? This doesn't work quite that way. There are these billions of nodes, trillions of parameters. Parameters are all these multiplying numbers, right? All of those kinds of numbers. And we can't, these machines are determining these numbers, right? So that's why these algorithms need very powerful computers to operate, because it is trying to keep track of all of these numbers, update all of these numbers, change all of these numbers, right? And so these very large algorithms, they are connected to resource consumption by the machines. They also eat up a lot of resources in order to store and process and work with all of these billions and trillions of numbers. But the thing is that if you have to figure out how some kind of a human drawing gets attached to a label like a cat without actually specifying what the rules of a cat are, then you need these many numbers in order to be able to do that calculation. And the funny thing is that if I ask, for example, people who are really trying to, like, who are actually modeling these systems, who are designing these systems, even they don't know what these intermediate nodes, what the hidden layers, what they are called, are doing, or if we can ascribe meaning to it, right? So you could, for example, ask, like, is this algorithm, all of that multiplication, could we just say that, somehow those multiplications of numbers or matrices in various cases, whether they're just picking out whether the picture has two pointy ears, a tail, whiskers, or maybe other very clever rules for figuring out if it is the drawing of a cat, right? And the answer is no, meaning no, some of these nodes maybe are designed in such a way, they're programmed in such a way, such that if I, for example, make a pointy little thing, like I make a little pointy, that looks like a ear of a cat, right? So maybe that node will get a high value if my picture has a little pointy bit like that, right? Some of these nodes function this way, but remember that there are billions of these nodes. And just because we have been able to figure out that one of those nodes, for example, or a few of those nodes are able to have some kind of a tie-up to, like, we can interpret what the output of that node is. Most of the output we can't interpret, right? And so what that means is that there is no meaning attached to any of these nodes. It is just a calculation, right? All of these multiplications, integrations, these all get performed, and at the end of it, somehow the machine is churning out matching probabilities in some cases, not all of the cases, right? Like, there's some cases where it makes a mistake, right? So, but then how does one know what numbers to multiply the original values with, right? Like, are the programmers sitting and programming in billions of these values? Well, no, actually these numbers, right? Like this 0.5, 0.6, this 0.5, these multiplier numbers, no, so programmers are not sitting and programming those in. There's a whole process by which that happens, and that is the process which is called machine learning. That is the process by which we are saying that the machine, that process, automation of that process by which those billions of numbers are assigned, is what is called machine learning, right? So the machine is learning itself, because at the end of the day, after these numbers have refined, the machine can say things like, oh, I know it's a cat, right? So that way we are saying that the machine has learned to recognize doodles, right? Sufficiently well, like, it's still making some errors, but sufficiently well, right? So how does that learning process work, right? So now again, the same machine that we were working with, imagine that, but instead of a player, what we have is a tester, right? And the game interface tells the tester, draw a cat. So the tester draws a cat, right? And that cat is input into the machine. And the machine, at this time, the machine, imagine that the machine is really bad. Machine is not doing well, right? In the sense that the machine churns out all kinds of strange random words for a picture like this, right? And so maybe it generates a ball and it says a plate and a potato, but cat is only 60%. So the output of the machine is not something that would be desired by a human being, right? Like a human being might want to say this is a cat, or maybe a dog, I don't know. But what is happening is, then we compare the cat with the top level ball, and if there isn't a match, which is in this case isn't, because what we want cat is at 60% probability, right? So at this point, instead of trying to output things like it'll just say the ball and then continue to guess or something, it tries to adjust these multiplier numbers. So it stops, right? The program has failed. Adjust the numbers. It adjusts the numbers so that the probability for the cat, this 60%, would go up by a little bit, right? It doesn't solve our problem completely. It goes up by a little bit, no? But you do this process thousands and thousands of times. So imagine testers who are sitting and doing this process again and again and again, millions of times, and over millions of times, all of these weights get adjusted so that the system is able to output a probability table that makes us go like, whoa, it guessed it's a cat, right? So it generates that wow factor in us. But it's because for thousands and thousands and thousands of times, somebody has been going around, and every time there's a mistake, the system then adjusts its weights, right? And there are various algorithms and various processes by which the weights are adjusted. I don't want to go into the technical details of that, because ultimately our purpose will be with ethics, right? But understand that these final values of these numbers, the training that happens, those numbers are an important specification of the model. And so those are prized secrets of these corporations. Right? Now, working with images, we can do the same thing with text. So imagine that a neural network, instead of trying to predict what the label for an image should be, it is trying to predict what the next word in a sentence should be. Or, for example, in the case of Copilot or something, what the next line in a code should be, or something like that. So imagine now a sentence like, the dog ran after the blank, right? And we want the neural network to tell what the next word is, right? So this input string, that is converted into various tokens, numbers. Imagine that is getting filled into the input layer. And then it does all of this mathematics of multiplying these numbers through these different layers. And once again, what we get is the output layer is the probability of what can be the word at the end of the sentence, or after the words, the dog ran after the. So the dog ran after the ant gets a 90% probability. The dog ran after the mosquito gets a 88% probability. And the dog ran after the cat got a 94% probability. And in order to do this system would have to be trained on a lot of text, right? So that the system can understand that in the data that it has already taken in, the pattern is such that the dogs run after cats and not mosquitoes or ants, right? Even though cat, ant, mosquito, they're all, well, our doodle is saying that they all look very similar, right? Like that the top choice is cat, ant, mosquito, but the dog doesn't run after them. So the text system will have to work a little bit differently for this thing to work well. But what happens in a chatbot? It just doesn't complete sentences, right? This, by the way, is something that you might recognize in your phones. Like very early phones had this sentence completion kind of a thing, right? But these AI chatbots, they are just doing this process on repeat. So what you can do is, you can do the dog ran after you make a prediction cat, and then you feed the word cat in here. So you say the dog ran after the cat, what will be the next word? And then you feed that in, and then you even if it is a full stop, then you get a full stop, and then you add a full stop, and what would be the next word, right? And so maybe the cat does something, right? And so those words will get generated, but all of those are getting generated by probability, because what would happen after the full stop? Maybe the word is the. How is the word the? Because maybe it has eaten all of this data where the pattern is that the is a frequent word after full stops. But what happens in all of these machines, again, is it's not like the machine is updating these numbers by itself. there's a lot of people who are getting invisibilized in the process. We don't get to see their work when we are only focusing on the machine. And for example, data workers, think about data workers. They are collecting data, they are creating testing prompts, right? To figure out, they will try to give really tough prompts to ChatGPT or other systems and try to see that are they generating harmful outputs, or maybe if we want to test how the system will behave on a variety of different things, data workers are the ones generating the prompts. They are then rating the machine output that the machine is outputting to these prompts. They are rating whether the output is good or it is bad. Oftentimes they are labeling data. For example, lots of images, they'll be labeling different parts of the images. What is a tree? What is a person? What is a car? What is an animal, right? You can imagine how that'll be useful if a system wanted to distinguish between a tree and a car in a driving system, for example, right? So they have to label data, and they remove harmful data and output, right? So they are monitoring the systems for harmful output. You saw that Amazon ChatGPT was hiring 40 people to remove the harmful output from ChatGPT, right? So real-time correction, they're doing all of this. And we don't get to see this work, and that's why Mary Gray and Siddharth Suri are calling this ghost work, right? This kind of work that is happening. And if we look more closely to the game that we just played, what do 50 million drawings look like? Well, over 50 million players have contributed to these drawings. No? So 50 million, and maybe each drawing takes about, I estimated maybe 10 seconds to draw. So that's 500 million seconds. That's a billion seconds almost, if I want to double, if I were to take 20 seconds or something, right? Or half a billion seconds. And when I was calculating, it ends up being 86 years, working 8 hours a day, 200 days a year. So that's the amount of time that we are ending up spending in order to create this database, right? And all of the users, we are generating this database. This is unpaid labor, right? And when data workers are doing it, well, sometimes it's still unpaid labor, but oftentimes it's underpaid labor, right? But there's other people's work that is also invisibilized. People who are miners. These systems require very big computers, lots of computing power. In order to power those computers, you need batteries. You need a lot of lithium for the batteries. You need a lot of cobalt for the technology. You need rare earth minerals, right? All of these are needed, without which we wouldn't have computers, these large, big computers, right? We need e-waste managers. As these technologies are coming in, a lot of people are also discarding old devices. These devices create a lot of environmental pollution. So there are people who are trying to handle the hardware waste that is being generated, right? In a way, some of these people are the climate warriors. And so all of this work is going into, when we sort of like look at this machine doing something like, oh wow, it can automatically fill in the sentence, the dog ran after the cat. Really, it's the work of all of those people that is behind the machine being able to do that. It's the intelligence of all of those people behind the machine being able to do that, right? So that's some of the design and production, and that brings us to some of the other points of demystifying things. This is not, so one, again, workers sustain automation. So they are the people who are doing this. The next point is, this is not how humans learn. We just saw, for example, the learning cycle of the quick draw, where some set of probabilities are generated, they are matched, and if there isn't a match, then system parameters are adjusted, right? And there is no evidence that humans learn like this. That is not how humans learn, right? When we look at learning in humans, learning is embodied, right? A child learns by understanding the gravity in the environment, dropping balls, pushing things, looking at how objects are behaving, how they are interacting with each other. It's a very physical, embodied thing that helps us understand about the physical world and how we learn, right? And even as we grow older, we are still using all our senses to learn, right? Like for example, right now it's not like you're using all your ears or your eyes or so on and so forth, right? All our senses are used in learning, and learning is emotional. It is emotional, it is social, it is relational, it is contextual, it's dynamic, right? We learn with other people, we learn in relationship with other people. We have strange relationalities with learning. Like somebody says that I really hate physics, right? And somebody says I really love physics, right? Or I had a good physics teacher. Relational, mediated by human relationships. And contextual, I might like learning in certain contexts, not in other contexts, right? It is connected to a sense of self. It is connected to aspiration. What I learn is connected to what I want to be in the future, in some sense, right? It's connected to this, and it opens up these possibilities. So learning in humans is very varied, and none of that is captured by this updating of parameters or how that is functioning, right? So that's how the machine is updating certain kinds of numbers, and human learning is not this set of numbers with hidden layers. That's not how human learning is functioning. Okay. What this system is doing is it's pattern matching. It is not meaning making. So it's just looking for patterns. How do I know that? Well, let's look a little more deeply. I tried to play with the system a little bit in a different one, and I thought, what will happen if I make this squiggly? What will the neural net generate? What will it think about, right? So it said, well, you were asked to draw a zebra. You drew this. It said neural net didn't recognize it, but it still gave me options. It was like the drawing looks like a raccoon or a shrimp or a garden hose. It is because the machine can't help it. You see, the neural network will have to generate numbers for the 345 labels it has. For every squiggly I draw, it will compute probabilities on exactly those 345 words, which include words like ant and road and ball and cat and raccoon and shrimp and garden hose, right? And it just so happens that my squiggly generates the highest probability for the word raccoon. And so they slap on, some picture of raccoon and some picture of shrimp that they have in their database, and some picture of garden hose that they have, or some doodle of garden hose that they have in there. But it's not phased at this squiggly. Like if I ask a child what I'm drawing, somebody might say it's just a scribble, right? But it does not have the option for scribble, and so it has to say raccoon or shrimp or garden hose. So that's what is going on here. So that's how I know that these are just probabilistic computations, right? And so what that means is that some of this language is also misleading, right? The neural net is not recognizing anything. It is also not thinking anything. If we are going to be more accurate, then we should be saying things like, well, you drew this. Well, I did draw this. And the label with the highest probability, as calculated by the neural network, matched the one that was assigned to you to draw. So there's a match, right, of the label that was assigned to me and the label that had the highest probability in the neural net calculation. There's no recognition in the sense that happens when, for example, you look at that picture and you can recognize a cat, but it's also funny, right? It's also funny, like what are those whiskers and what's that one pointy ear? Where's the other ear of the cat, right? We can experience some of that humor. We can experience some of the absurdity. Even in the other sketches, like look at that mosquito, right? What does that make you feel? What does that make you think? And the neural network does none of those things, right? So it's not recognizing. It is just that its computation has generated cat as the label or the word with the highest probability, right? And so it's also not thinking. So what should we say? We should say the three labels with the highest probability as calculated by the neural net were cat, ant, and mosquito, right? And it should accurately say an illustrative sketch is shown for each label, right? That's what is happening. So it's not recognizing its pattern matching. And here's an interesting study that happened where people were trying to automate skin lesions. They're trying to look for cancer cells on the skin cancer, and trying to get a machine to tell if the particular lesion is cancerous or not, is it malignant or not. And here's what the authors say. This got a lot of press. This was in Nature when it first came out, and then the authors are saying later this. We noted that the algorithm appeared more likely to interpret images with rulers as malignant. So if we look at some of the images, you will see that along with the image of a tumor, there's all of these little little lines. That's a ruler, right? And so the authors are saying that the algorithm appeared more likely to interpret images with rulers as malignant. So if there was a ruler in the picture, it said that the tumor is malignant. It was a very successful algorithm overall. But why? In our data set, because in the data set, images with rulers were more likely to be malignant. And thus the algorithm inadvertently learned that the rulers are malignant. So what is the algorithm doing? It's just figuring out these patterns in the data. Right? And if the pattern in the data is that malignant tumors have a ruler in the picture, then it will pick up that pattern. And then if there's a ruler in the picture, it is more likely to say that it is cancerous, even if it is not. Right? Similarly, here's another article, this also from PubMed. This is Beyond the Hype, Navigating Bias in AI-Driven Cancer Detection. In this case, the authors are saying that the accuracy of an AI-based model relies on the data on which the model has been trained. And this means that if the initial data sets are not representative of the population where it will be used, it would ultimately impact the performance of the test and affect generalizability. Right? So here's a simple way to say it. For example, if an AI model is trained on Caucasian patients, meaning white patients, it may struggle to detect skin cancer in patients with darker skin accurately, leading to missed diagnosis or false positives. So the stakes are really high. No? Because what it is saying is that if the data on which it is trained, for example, has more white people, then it will be a model that maybe is going to produce a lot of errors for when the skin of the person it is diagnosing is not white, right? And these kinds of biases get baked into the data, right? Baked into. Why? Because the technology is just doing statistical pattern recognition. So right now, that's the point that I'm trying to make. It's doing statistical pattern recognition. And if the pattern happens to be racist, then it will reproduce that racism, right? And machine output can be incorrect, not just biased. We saw, for example, well, in the case where I drew right in front of you, it got all right. But in another case, it had gotten 4 of my doodles right. So there was 67% success rate. It had gotten 2 out of 6 incorrect. So that's a 33% rate of failure, right? And sometimes AI can have similar rates of failure in other kinds of things. So here's some very hot of the press. I just saw this today, where BBC is doing a study on integrity of AI assistants, right? So these AI assistants like Copilot, ChatGPT, Perplexity, Gemini, and they were asked particular questions, right? And then their output was rated by experienced journalists as to whether there is some issue with the output, with the accuracy of the output, or there's significant issues with the accuracy of the output. And here's the results. What the overall is saying is about 20% significant issues with the accuracy, and then another 40% is some issues with the accuracy, for total of almost like some, nearly 60% issues, having some kind of an issue, right? And so this is what is, when we benchmark the output of the ChatGPT or Perplexity or Gemini on particular topics connected to journalism, and journalists are looking at that, and what we are seeing is that much of issues that are existing with this. So the question really becomes that, maybe we are okay with having error in our news, or maybe we are not okay with having error in our, how much error can we tolerate, right? When the stakes are really high. So, for example, when courts are using it, right, the stakes are really high. When the police are using it, the stakes are really high. When banks are using it, the stakes are really high. When they can influence election systems, the stakes are very high, right? When they can spread misinformation, the stake in a society, the stakes are very high. So how much error can we tolerate, right? And I'm not giving a number. This is for all of us to sort of like think about that. Here are these automation technologies. They are statistics based. They're just looking for patterns, right? And they're designed to look for patterns. They're advertised as intelligence, but they're really based on the work of thousands of workers in low paid exploitative conditions, right? They are, at that case, when they are being used in these really high stakes environments, what error are we willing to tolerate? That's got to be all of us to think about. With that, I want to come to my talk to an end and see what questions there are, right? Because the next, on Friday, we will go into what does that mean for ethics of technology. Once we have of AI technologies, now that we have understood this thing, let's go deeper into some of the harms that come up when the AI technologies are creating errors, or when they are exploiting workers, and so on and so forth. Let's look at some of that more closely on Friday. Awesome. So let's look at some of the comments. Hi Flame, there's a comment. Other than LLMs, what other types of AI models are used in daily life? And like, how are they different from the algorithms we used to use before, right? Example, I see AI integration in products like AC. So what is that, right? So AI technologies can actually, and a lot of different kinds of technologies are based on AI technology. So for example, if we are thinking about an AC, there could be some kind of a system in the AC that is trying to monitor, for example, how the AC switches on and how the AC switches off. And so maybe it takes a lot of different kind of sensor values, right? Maybe it is fitted with various kinds of sensors, and then it can take those values, and then it can regulate your AC temperature, humidity. You can set it up to do that, rather than trying to set the humidity level and temperature levels on your own. You may want to automate that. So that is one way that you can be used, right? There are varieties of other ways, like in washing machines. Similarly, you can see AI integration, right? They're all trying to say, let's take a lot of data on how machines are functioning, and then we will look for patterns in the data that will tell us, how we can automate some of the processes in the machines, right? So for example, if I want to understand, so here's an example of a washing machine. So a washing machine needs to wash the dishes, and suppose I just set a cycle that is a 30-minute cycle. Maybe the dishes don't get washed, so then you can say, well, just set it for 45 minutes, right? But maybe still the dishes don't get washed. What if there was an artificial intelligence that could determine when the dishes got washed, right? For that, you will have to, for example, fit in sensors that will be able to tell how clean the water is looking. Maybe it also is aimed at some of the dishes and does some spot checking to see if, are there any, it can do image recognition. So it can take in that image and it can maybe look at whether there are food spots on it, right? Or some sensor that is being able to detect whether the water is clear or turbid, right? And it can feed that information back into some system that is then being able to make a decision, right? But again, many of these things are also getting honestly advertised as AI, but many of them could just be intelligent control, like some kind of a complicated control system, right, that is taking in sensor input data, and it is doing certain kinds of calculations, and it's plain old automation. It need not necessarily be based on this whole big statistical modeling kind of a thing. So part of the model, part of the problem is that, algorithms are being used in various kinds of places, but AI advertisement is also happening in lots of false kinds of ways. Okay. If we don't know how the machine assigns, one more question from Fame, assigns these numbers or values, how did we figure out that this way we can make neural networks? Was it by chance, and how do we know it's giving correct output always? Right? So part of it is that, it didn't sort of like just get born that way. People have been working for decades, and they started with something really like a smaller kind of a thing. So can a machine recognize a triangle? Right? Just that. All it will do is it'll recognize a triangle. That's what we need it to do, right? Any other shape is fine, but if it recognizes a triangle, something like that, something really small. And then the idea being that, can we, for example, create one of these layered machines that will be able to do that. So where does this idea come from? Historically, because part of the motivation for these technologies is people were interested in, can machines think, right? Can computers think? Can they be made to think, right? And so various kinds of things happened. People started modeling humans in terms of computers. People started modeling computers in terms of humans, right? All of that kind of development ultimately led to some kind of a hodgepodge where people started thinking that these green nodes in these machines, they are like neurons because they can fire or they cannot fire. And just like our neurons get inputs and then they, create an output spark or not. And so people started thinking that these green nodes with these incoming links and an outgoing link, they are like a neuron. So all of that is metaphorical language. None of that has sort of like a real parallel. Maybe historically it was an inspiration or something, right? So that's a little bit of the history of it. But how are these values then assigned? Well, a lot of times it will be like, you may start with certain kinds of initial input. So you initialize the machine in some way with some kind of rules, right? And you know that the output of the machine is not going to be satisfactory, right? But what you do is you keep running that machine again and again. The output is not satisfactory, so you change the numbers a little bit, right? And there's some mathematics that goes into how you will change that numbers and which numbers you will change in any given moment. But you keep testing that system again and again and again. And every time it gives an error, you update the system. And you keep doing that again and again and again. And after thousands and thousands of times of doing that, those numbers will end up settling. And if they're not settling, you basically start creating more of these links. Like, there was this time when people threw a sort of like a challenge that, can machine learning people detect, classify images in a big, large image data set. And people tried all kinds of things, right? And it just happened that people who were trying out neural net kinds of ideas in order to do this, they ended up being successful. But you can do these statistical calculations in all kinds of ways, right? For example, trying to figure out where the average of a data set is. We can do that by quite simple software, no? But as you get more complicated statistical processing of this data, then there are more complicated statistical tools. So people have been doing, for example, facial recognition even before neural networks were there, right? Other statistical models and other technologies were being used to process the data. Neural networks are something that have become very famous now, partly because of the advertisement cycle of ChatGPT, right? Because some of the folks that were involved in the production of this OpenAI and ChatGPT and these kinds of things, right? Like, were also the originators who won this neural net competition. Geoffrey Hinton was one of them, the Nobel laureate. So it ends up getting the hype, and people put a lot of resources in it. And if you connect up this machine in this way, then somehow it gives you the correct output. Why does it give you the correct output? And what is that machine doing? Nobody knows, and you can't tell. Okay. Okay, folks. We can close the webinar. Thank you so much for attending, and bye bye.